Therefore, the probability of being in the typical set if that's less than or equal to 3 delta, the probability of being in the typical set is greater than or equal to 1 minus 3 delta. So because delta can go to 0 as n goes to infinity, that means the probability of being in the typical set goes to 1. In other words, it's valid, there exists sufficiently large n so that you can pick delta to be any value you want. So if you set delta arbitrarily small, there exists n sufficiently large so that that's possible. So therefore, as n goes to infinity, we can say that the probability goes to 1. Okay, so what that means is, if I select, the selected sequences are members of the typical set with probability 1. So that's much like the asymptotic equipartition property for sources, where if you observe a sufficiently long source sequence with probability 1, that source sequence is in its typical set. Okay, the second statement, let's remind ourselves what that was. Cardinality of the typical set is less than or equal to 2 to the n h of x and y plus epsilon, and for sufficiently large n, the cardinality of the typical set is greater than or equal to 1 minus epsilon 2 to the n h of x and y minus epsilon. So, the argument is exactly the same as for the marginal typical set, but let's review that argument. So, prove this statement. What I'm going to do is I'm going to prove the upper bound. The lower bound is proved in basically the same way, but you can review the details in your notes from what we talked about, because proving the upper bound is sufficient to probably remind you. So, 1 is equal to the sum over x and y of all possible x and y from 1 to n of the probability of x1 to n, y1 to n. So all possible sequences, the total of their probability is 1. What we then do is we split this up into things that are in the typical set and things that are not in the typical set. So this is the term of this sum that's in the typical set. I'm going to put a bar here over the typical set to indicate complement. This is the term that's not in the typical set. And the approach is I throw this term out and I say that therefore this term is greater than or equal to just the probability of the typical set. So that's true because probability is positive. This came up from the marginal typical set, but one consequence of the definition of the typical set is that the probability, and you can review this in your notes, for any sequence in the typical set, the probability is sandwiched between 2 to the minus n h of x and y minus epsilon and 2 to the minus n h of x and y plus epsilon. So that was one of the properties of marginally typical sets, and it's also true here. So what I need from here, this is less than this probability less than or equal to just considering the typical set. Continuing that chain, this is less than or equal to the sum of all the members of the typical set of the lower bound on probability, 2 to the minus n h of x and y plus epsilon. Now, the number, this term is now independent of x and y, so therefore I can take it out of the sum, and I get 2 to the minus n h of x and y plus epsilon, sum over the members of the typical set of 1, which is equal to cardinality of the typical set times 2 to the minus n h of x and y plus epsilon. So therefore, cardinality of the typical set times this is less than or equal to 1. So therefore, if I divide both sides by this, that means the cardinality of the typical set is less than or equal to 2 to the n joint entropy between x and y plus epsilon. Now, the lower bound is proved in much the same way, except then you use the upper bound on probability, and you use the weak law of large numbers, and that's where the 1 minus epsilon term comes from. And I'll let you look that back up in your notes from when we were talking about sources.